Welcome everybody, it's Ramachandra from CIVIL-MECH-MATHS Concepts, and this channel is started by me for the benefit of GATE aspirants, SSC JE, UPSC, Engineering Services Examination and also Civil Services Examination, and also for PE and FE, Professional Engineers Examination abroad. I have taken a very good example for the last 5-6 videos, and that example is this one. Combined bending and torsion in beam. Question is to have a balance of equipment in a factory. The maximum bending stress allowed in a sine wave shaped cross section beam is treated as the limiting stress in the premises. The details of the cantilever beam and the sine wave shaped beam are the equipment for finding the maximum stress is in sine wave shape. Sine wave shape is taken and maximum allowable stress is calculated for the maximum height of 300 mm, breadth 900 mm and 2 meters length, carrying a UDL of 1 kN per meter. The sine shaped curve beam is placed such that its breadth is horizontal. This we have solved in the previous to last video. The UDL is along the length. This is one information. Next is the cantilever of circular shape beam to be designed is 1 meter of length. There is another beam which is a cantilever beam. This beam is a simply supported beam existing. We have to design a cantilever beam taking the limiting stresses from simply supported beam, and the cantilever beam, new beam is 1 meter of length, 50 mm diameter with X load applied. Because we know the limiting stress, we can know what is the maximum amount of load that can be applied at the free end. That we call it as X. And we have to calculate it. That we have calculated X as 1.1 newtons. We have found natural frequency also we have calculated, that is as 35 hertz. Taking self weight into consideration, that also in the last class we have seen natural frequencies, and now these two are completed. If self weight is not taken, it is frequency is very high, almost equal to 8 to 10 times. Whenever the load applied is significantly lesser than the self weight of the beam, it is always better to take the self weight into consideration. This is one of the practical knowledge for the civil engineers. The question in the examination can be like this: under what considerations the self weight has to be taken into calculations, under what conditions? The condition is that if self weight is significantly higher than the applied load, or applied load is significantly lesser than the self load, then self weight has to be taken into consideration while calculating the stresses in the beams. And we have calculated almost 61 videos are released. We have calculated on structural analysis. This is the 16th lecture, and we have calculated and formulated many formulae from trusses to the beams and stresses. We have come to the stage of stresses. And on a Mohr circle also, I have released a short also on Mohr circle, principal stresses. Please see that also. Now, please see my previous videos for further understanding. In this lecture, we will be solving the question number C. What will be the maximum strain gauge reading in microstrains? To find out the maximum strain gauge reading, what we require, we have to know the place where the maximum strain takes place. And we have to know about the distribution of the strain in the beam cross section. We have to know about the strain diagram. For that, I have shown in the first page, this is the strain diagram. This one, this is a cross sectional area. In this, beam is given as circular beam, circular cross section. Beam is cantilever. And strain diagram is this. On the top it is subjected to compression, minus is compression. In the bottom it is subjected to tension, tension is plus. And when the movements are like this on a beam cross section, this is the beam cross section. If the movements are like this, then top will be compression, bottom will be tension. And we have found out the center of gravity, neutral axis. This is the neutral axis position. And because of the symmetry of the circular beam, the neutral axis and center of gravity both will be same, and this will be equal to d by 2 from the bottom of the beam. From the bottom, the geometrical center and the neutral axis will remain same. This is d by 2. This is the point where neutral axis passes. And because beam is showing a bending like this, at the bottom the beam is subjected to tension, and at the top it is subjected to compression. The beam is showing neutral axis is passing through the center of the circular beam, and at the bottom tension is there, at the top compression is there, and neutral axis is passing through center of the circle, circular cross section. This is what we have already derived, explained in the previous classes. Now let us talk about the strains. Let us talk about the strains. Let me change the template. Give me a minute. Let me change to ruled paper. Now, we know the maximum bending stress. This is maximum, sigma maximum is equal to maximum bending stress is equal to $86.207 kp, not kp, it is maximum stress is equal to sigma max. We have already calculated. $86.207 kPa. Yes, I am right. Now, this is the maximum stress because of the bending moment. Where the maximum bending moment will be there? Where will be the strain? And where will be the strain gauge required? For a cantilever beam, please go back to your basics. Whenever there is a point load P, the moment will be 0 at free end, and moment will be maximum at fixed end. This is a negative movement. And this movement and other calculations are made already in the structural analysis 12. Lecture number 12, structural analysis. I am going to give you the link for the playlists so that you can go back to the previous classes and learn from them. And we know the maximum bending stress that is caused to the beam is 86.207 kPa. Now, from the Young's modulus, we know that Young's modulus E is equal to stress by strain in the linear portion. We are talking about elasticity range only. Stress we know 86.207 kPa. Strain we do not know, that is strain. Implies what is the Young's modulus? It is constant for a particular material. That is Young's modulus is 200 GPa. For steel, you please make a note of various Young's modulus for different materials. It is always better. For aluminium, it will be around, it will be better to have them known to you. If you are doing one particular problem, either in GATE or somewhere, and if you have any confusion, you can cross check with the values what you have got, what is in your mind. So that for steel it is around 200 GPa, for aluminum it is around 70 GPa. Please note, usually these are the metals which being used. Now, here steel is being used. Now, E is equal to 200 GPa is equal to stress. Stress is 86.207 kPa. Let us convert everything to PA next moment and divided by strain. Strain does not have any units because it is a relative quantity, because strain is equal to elongation, linear elongation divided by original length or gauge length, we will call it as either gauge length. This elongation is in meters, gauge length is in meters, then it is unitless, dimensionless, rather we can say dimensionless quantity. Dimensionless quantity. Strain is a dimensionless quantity. Now, we got the value of Young's modulus, we got the value of sigma max. Strain is denoted by epsilon max, let us say. Epsilon it is called as. Epsilon is a strain. Now, epsilon is equal to E by sigma. From this equation, what is E? 200 GPa. What is sigma? 86.207. Strain is equal to, sorry, a little error while explaining. From this equation, we get epsilon is equal to sigma max by E. Sorry for it, very sorry. This is a very important equation. You should know it, because if sigma max is given and Young's modulus is given, it is easy to get the strain. If strain is given, stress is given, then it is easy to get the Young's modulus. Either way, the question can be made in the examination. Now, what is the epsilon here? Epsilon is equal to sigma max is 86.207 kPa is 10 to the power of 3 pascals and E is 200, GPa is 10 to the power of 9. You see, 10 to the power of 3 is K, 10 to the power of 6 is million, M, kPa, MPa, 10 to the power of 9 is G. Please remember this. These values are very, very important to remember. Now, you just see what happens to epsilon. Epsilon is equal to 86.207 into 10 to the power of 3 divided by 200 into 10 to the power of 9. That is going to 10 to the power of 3 by 10 to the power of 9 is going to give you 10 to the power of minus 6. That means 86.207 divided by 200 into 10 to the power of minus 6. 10 to the power of minus 6 we can write in micro units. That is micro strain. Usually strain gauges are made for measuring strain in, these things are very important, micro strains. That means in the multiples of 10 to the power of minus 6. Usually this is a practical thing. In market we will get micro strain gauges. This can also be a question in your examination. You may get strain in different units, different values, but in market the strain gauges read the micro strains. Please remember this, micro strains. Because in the question also I have given micro strain gauge reading. I wanted micro strain gauge reading. Now, what is the strain here? Strain is equal to 86.207 by 200 into micro strain. Mu is equal to micro. 10 to the power of minus 3 is equal to milli. 10 to the power of minus 6 is equal to micro. That is denoted by mu. That means 86 by 200. How much it is? 0.43. 86.207 divided by 200. 0.431. 0.431 micro strain. This is the answer. In micro strains, the strain gauge reading will be 0.431. That is the strain gauge reading. And if it is on top, it can be either compressive or tensile in nature, depending upon the geometry given, depending upon the forces applied. The strain diagram will be like this. I can write, first let me write it is always better to practice like this. Let us draw the cross sectional area of the beam. It is beam cross section. Then we will go for the along the diameter we have got negative side is compression, positive side is, because it is in the center, this is positive tension, negative compression. This is the strain diagram. And this is the neutral axis. and extreme fiber strain is epsilon maximum tensile strain here, epsilon maximum compressive strain is here. And if you want strain at any particular point, let me say at a distance of y from here, then this will be, because it is down, it will be a tensile strain, and the strain will be here. The strain is this. You can calculate from the triangle the strain at a particular distance from the neutral axis. Y is the distance from the neutral axis. Similarly for compressive strains. That means this is the strain distribution and this is the beam cross section. This is how we can calculate. The value what we have got is, value is not that much important. The procedure should be understood well. Strain, micro strain. This is the strain gauge reading what we have got. With this, today's lecture I want to stop. In the next lecture, I will take about the deflections of the beams. That I have to find out the maximum deflection in this particular case, but instead of this particular case only we have to do, before solving this problem, I want to give a brief about the deflection of the beams. We are able to know about till now bending moment, shear stress, bending stresses, and then strains, strain diagram, stress distribution, strain distribution. Now let us know about the deflections in the next class. This problem will stretch because it is a very big problem which I have taken up intentionally for the benefit of all of you, so that with one single problem you will be able to cover the total syllabus of beams, stresses, and then your bending stresses, strains, strain diagrams, stress distribution, strain distribution, beam theory. After completing the deflections, I will talk about deflections in cantilever beams, continuous beams, and then simply supported beams, fixed beams. Then we will switch over to this final problem, final question, find the maximum deflection. Then we will close these beams. Then we will go to the topic of shear stress. After deflection, we will go to the topic of shear stress. And afterwards, we will go to loading of torsion. Then once loading, then combined stresses in the beams. That is the way we proceed, so that we will complete the structural analysis of the beams, stresses, bending stresses, torsional stresses, and then your shear stresses, and then deflections, bending moments, shear force diagrams, and for bending moment, shear force diagrams, and bending stresses, and all these you can refer to my previous lectures on structural analysis. About 15 lectures are already released. My channel name is CIVIL-MECH-MATHS Concepts and I have released certain playlists, 5 playlists. I will be putting this video in all the playlists, and I give the link of the playlists also. So that you can see the world lectures, world videos. Around 61 videos are released till now, and the lectures include even engineering mathematics also, which is required for structural engineering. You can refer to engineering mathematics lectures also. Best of luck to everybody. Thank you for listening to me. It's Ramchandra again from CIVIL-MECH-MATHS Concepts channel. If you feel there is value addition to you with my videos, please subscribe to my channel, view my old videos also, share, review and view. Thank you for listening to me, and I have released some 2 shorts. One is YouTube shorts, one is on eigenvalues, finding in seconds, and second is finding the principal stresses using the Morse circle. Finding principal stresses using Morse circle. One YouTube short is there created by me, released by me. Morse circle in less than a minute. It will be very useful for SSC JE, GATE and competitive examination aspirants. Best of luck. Thank you. Please see my shorts also. 2 shorts are there. One is on eigenvalues, another is on principal stresses. And 61 videos are there, and about 16 videos on structural analysis. Please see them.